Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about something called directional derivatives and the gradient, which are two very, very important concepts in Calc 3. To start off though, I want to do just one of these implicit derivative problems. So I have this function right here, which is implicitly defined, and I want to find the partial of z with respect to y. So I'm going to start off, I'm going to set it equal to 0. So basically I've got like f of x, y, and then this is like a function of x, y, and now it's equal to 0. And that implicit function theorem just says this thing equals negative capital F of y, f sub z. So f's with respect to y is going to be z plus x over y, and then there's no y here, so we can just ignore that. And then this thing with respect to z now is going to be y, then there's no z in here, so then just minus 2z. And you could simplify it if you want, but that's fine. So that would be it. I don't know why I'm circling all of that. I want to circle that. Okay, on to this stuff. So directional derivatives and gradient are very, very, very big. Basically, this is where I can finally talk about, the true idea of a derivative in three-dimensional space. Because up to this point, we only had partials in different directions, like specific directions, x and y, maybe z, if it was like a four-dimensional problem. But that really clearly is not as useful. Like, we might need to know, like some sort of landscape like this, we might want to know which direction maybe is the steepest, gradient as we go up, like which has the steepest ascent, or maybe we just want to know how steep it is, like along like the side of that mountain or something. Maybe we're building a road and we need to know, based on the steepness of that hill, we need to know like what to cut it at or something like that. You can also think about it like with weather, like might want to check the temperature change in like a specific direction, like from here along this line. You can see that faint line there. Like it could tell you something more important about the front of like some storm or something like that. But basically the idea is like this picture really. This is just like the top view of that. What we're going to basically do, and this might help too, is we're going to be checking like the rate of change of things in different, they could be temperature, elevation, whatever, but in different directions. So not specifically x and y. It could be this weird direction here. Something like this, where it's like there's some surface and we're checking, the slope along, like some sort of curve in this random u direction. That's the idea, which is obviously much more important. Sometimes checking the change in x and y is important, but a lot of times you need to check it in like a specific direction. So the idea is basically this notion of a directional derivative, and we basically need to figure out how to get the magnitude of like the partials of x and y in the direction of some like u vector. So u could be like this red vector right here. That's just pointing in like arbitrary direction, right? Not x or y. And this is like a vector right here that's built out of my partials in x and y. And if I could figure out how to get the magnitude of this showing up on here, that would truly represent the slope in the direction of u, which is then like the derivative in u's direction. And this is something, it should look pretty familiar. This is why I actually have this here. So you should be kind of thinking projection, because basically that's what we're doing. We're kind of seeing how much of this shows up on this thing. But we want to know specifically magnitude. So we don't want to just project the vector. We want really what is called scalar projection. And it turns out, so this is kind of deep and beyond maybe what I really want to get into, but if you have some vector like v and you dot it with like some vector w, then in conceptual terms, what this actually means is it's like the length of the projected v times the length of w, right? So this is a scalar. A dot product is a scalar. It's a number. It's not a vector. But if you do a dot product, it's really interpreted as the length of the projected vector, like some vector on, the length of that projected vector times the length of whatever vector was there already, okay? And technically you can actually do this both directions. So you could even think of it as projecting the u vector onto here, and then times the length of this vector. But it turns out that that's basically the magical thing. That's this scalar projection. So it is like a very special projection that actually is behind the scenes really whenever we do a dot product, is this scalar projection thing. And I don't want to get into it too much because it's going to cause too much confusion if I really dig into the weeds there. But the idea is we can figure out how much of this vector right here there is in this direction u, if we literally just do that dot product, because it's really a length of that projected vector times the length of w, and it's going to give me a number, and that number is going to be literally like the rate of change in that direction. And this vector of like the partial derivatives is something that we call this is something called the gradient. Okay, so let's do, I don't know, I'll do this. So this is the weird symbol we actually use for this thing. This symbol right here kind of looks like an upside down delta. It's actually nabla. And the reason they call it is because I think in Greek, but don't hold me to it, you can kind of think of it looking like a harp is the idea. And that word has something to do with the word harp in Greek, I believe. But nabla of f is defined down here as this derivative of, or this vector of partial derivatives. And when we dot that vector of partial derivatives with a unit vector, and specifically this is always a unit vector, because it's really just there to give me the direction of that vector. I don't want to actually make it bigger, so I want the length to be 1. Then if the length is 1, then I truly get the notion of how much of this derivative shows up in that direction is the idea. And this is the notation we use, that it's the derivative of f in the direction of u. It's kind of how you read it, derivative of f in the direction of u. So I'm going to show you one, but that is kind of the nuts and bolts behind the scenes, and I didn't write it, and I should have written it. This symbol right here is called the gradient. It's a very important word to know. That nabla f thing, that vector is the gradient. So this is the vector down here. That's the gradient. The gradient is a vector. All right. So find the directional derivative of that function at that point in the direction of the vector 2, 5. Okay, so one of the things that I see as a common mistake is students just jump in and dot it with like the vector in the direction, but if you do that, you're actually getting more stuff, more of a derivative than you really want. You want to dot it with a unit vector just purely to get it to point in the right direction is the idea. But you don't want necessarily this vector. You just want to make sure it's length 1. So just to start off, I'm going to figure out u, which is a unit vector, so I can put the little hat thing on it. And I'm just going to do v divided by its magnitude. So the magnitude is square root of 4 plus 25. And then it's going to be times the vector 2, 5. And the other part of this that we're going to need is this gradient thing. So that's sort of my unit vector part, and then my gradient part. The gradient is a vector. Gradient of f is just basically a vector of all the partial derivatives. So like that. And so I got to go ahead and take my partial derivatives. So f with respect to x is 2xy cubed. F with respect to y is 3x squared y squared minus 4. And then we are told that it's at the point 2, negative 1. And so if we go and do the gradient of f at 2, negative 1, we get negative 4, 8. All right? So now, putting it all together, this thing over here. So the directional derivative of f at 2, negative 1 in u's direction is literally just the dot product of, I'm going to do this kind of version of a vector. So negative 4, 8 dotted with 2 over the square root of 29, which is the magnitude, right? And then 5 over the square root of 29. And if you do that out, you should get 32 over the square root of 29. All right. So the good news is that gradient and directional derivatives scale really nicely into higher dimensions. So they actually work for all like Rn. So I'm just going to do another example. Basically, it's the same example as the last problem, but just to show you like how it works for 3 inputs. So it'd be like a function that maps spatially into the 4th dimension. So you have 3 inputs, right? And so we'll have f with respect to x now and y and then z. And then we just literally dot that vector with this unit vector, which we'll get from here. So let's do the unit vector. It's going to be 1 over square root of 1 plus 4 plus 1, which is 6. And then, so that is my unit vector. Which really was just v over the magnitude of v. And then the gradient of f is going to be this vector of all the partials. I'm going to do this kind of vector. So so for the first, f with respect to x, we can literally just copy down the sign part because the x just kind of drops off there. And then we'll do chain rule for this other part. So we're going to get like x z sine, cosine yz for f with respect to y. And then lastly, we would get x y cosine yz for f with respect to z. So then I'm going to go ahead and like evaluate that thing at the point 1, 3, 0. And we would get that because you basically, if you just plug in, z equals 0, here you get 0, and then here you get 1 and 1, and then, but there was a 0 in there. So 0, 0, and then 1 times 3. So now we just go ahead and do the dot product. So we've got, let's do it down here. So we have 1 over square root of 6, 2 over square root of 6, negative 1 over square root of 6, all of that dotted with 0, 0, 3. And it's always nice when you're dot product with 0 because you can basically just ignore them, and then you would get that as the directional derivative of f at that point in the direction of 1 to negative 1. So I think this next example will help clear up a little bit about what we've been doing before. So it turns out that actually we've basically just been always doing directional derivatives. So if u was like if the specific unit vector was I hat, okay, then when we do the gradient of f dotted with u, right, we would be doing, let's do this. So we would be doing f with respect to x, f with respect to y, f with respect to z, dotted with 1, 0, 0. And you can see that when you do that, you pull out just f with respect to x. And so we sort of like started here and just ignored all this. But technically, this has actually always been what's happening. We've always been doing this scalar projection, which really works out to just be this dot product here between the gradient vector and specific unit vectors. And like you could do the other one. I'll just do one more. So if you do like gradient of f dotted with, say, j hat, right, you can just see that the only component of the gradient that stays around is the partial of f with respect to y. So that's just kind of a good like conceptual thing to see that like actually the partial derivatives we've been working with are truly just directional derivatives, just directions in, along the axes we're used to. So a really important other concept question is just one down here. So related to our direction vector u, when would a directional derivative have its largest value, and what would that largest value be? So if you think about what we're doing, we're basically having some sort of like unit vector, and we have this gradient function, vector, I keep saying function, and we're basically doing this like projection thing down onto that unit vector. But when we do that, right, this resulting kind of projection right there, that vector is smaller, right? It's not the hypotenuse of this triangle. It's one of the legs. And so that, in a sense, sort of acts as a, like, loss of slope, I'm going to say. We kind of lose some of the derivative. So the idea for maximizing the directional derivative is basically if the unit vector and the directional derivative align perfectly, right? So what direction, related to our direction vector, what direction do we need to point in? Basically, it needs to be in line with the gradient. And then we, in a sense, don't lose any of that slope, is the idea. And the largest value would literally then just be the magnitude of the gradient of f. So, as for like this last part right here. So that the largest value would be the magnitude of the gradient of f. If I literally go back to this idea, this now is sort of been maximized in a sense because that projected vector is at its biggest. It is the hypotenuse now, right? I don't have it being the leg of a triangle anymore. So I actually can just take the magnitude of the gradient, and that is the measurement of the steepest. This will basically sort of represent the steepest slope change. And steepest slope change could be both positive and negative, right? It could be like steepest downhill or steepest uphill on some like mountain, or it could be like the most temperature change or the least temperature change, or like the best way to increase money for a business or the worst way to increase or decrease your money for the business, right? And this kind of stuff is something we use actually quite a bit. So I'm actually going to skip that for 1 second. I'm going to come back. But I wanted to talk about this first. So just because it builds off of that very nicely. So there is something in optimization. So this is like a huge area in tons of technical fields, but something called gradient descent. And the idea is if you just follow the way the gradient is pointing at any point, then you should always be able to get to like a local maximum or minimum. So if we, sort of think like, let's take this 2D picture. I think this is the easiest one to see. So if we are literally perpendicular to that, this would be the gradient, right? Because if this is like the elevation change, to like go uphill as fast as possible, we would go perpendicular across that line. We wouldn't want to angle it or something, right? Like if we walked along this line, we're always at the same height. So we would want to walk straight across it, like perpendicular. And that would be the gradient. This would be the gradient. And then if you keep following the gradient, like right there, and then right there, and then right there, and then right there, then you get to basically the summit, which is like a local max for some surface or something. And you can do it the other way too. You can start up here in the high kind of elevation areas, and you could follow the gradient, and it'll take you like basically to a local minimum. And we use this all the time. Like there's tons of things in math and science we want to optimize. It's a very common problem. And this is just another picture of it. Like this might represent the like a cost function or something, where we want to minimize the cost of some sort of thing. So cost can actually be like interpreted with artificial intelligence has like a cost function. It could literally be a financial problem. You could have like some sort of surface, they don't need to make sense. This is just like saying that like some financial problem has like two inputs, so we get a surface technically as like the output of what it looks like. But it could just be like we're trying to minimize the amount of money we spend, for our business. Or we want to minimize the, errors in our artificial intelligence kind of code. And so that could represent like a cost function that we just follow the gradient on. We do gradient descent, as a technical term, and we would get to the bottom. All right, so I just want to go back here. So this is basically just summarizing what we were just talking about. So assuming a non-zero gradient, okay? So the directional derivative is maximized when that unit vector points in the same direction as the gradient, and the max value is the magnitude of the gradient. Likewise, that directional derivative is minimized when the unit vector points in the opposite direction, of the gradient, and the minimum value is negative of the gradient, right? So basically it's just saying like if, this is the most rapid decrease is if you go like negative gradient f vector, and most rapid increase is going in that way, in the direction of the gradient. These would be zero changes, it's saying, right? If you go perpendicular to the gradient, that would be a zero change in f, which might be also important for some like physical problem or something. And I'm just going to kind of like sell you on this a little bit. I'm not going to do like a super rigorous proof, but I'm going to start with the cosine formula for like vectors, right? So we know that the cosine of the angle between two vectors is the dot product of those vectors over the magnitudes, right? And so just rearranging, I'm just going to like multiply like by the magnitudes on the bottom. So we have gradient of f dotted with u would then equal cosine theta magnitude gradient of f magnitude u. The u magnitude of u is a 1, right? That's going to go away. And the so this is my the given problem is that u points in the same direction as the gradient. So that just basically, this part right here tells me that theta equals 0, right? So that implies that this is 1, which is nice. So now, if you look at what this is saying, this thing, which really is just the directional derivative of f, it equals the magnitude of f. And that would be its largest value. And the smallest would just be the negative of it, right? So that's just kind of like where it comes from. It really just comes out of that cosine vector formula.